Hi, good morning. Are there any questions? All right. Sorry, I don't know what's wrong with the microphone, but all right. We talked about theorems, relative theorems, absolute theorems. Let me just remind you what we talked about. If gamma is a set of formulas that we call hypothesis, we use this notation gamma proves A in order to denote that gamma can be applied as a set of hypotheses in order to give a proof, which is a sequence of formulas that you could obtain A from it. In other words, A is a gamma theorem. That's what we call it, right? A is a gamma theorem. And if the empty set, meaning with no hypothesis, you can prove A using only axioms and rules of inference, we call A an absolute theorem. Here in this case, A is a gamma theorem. You could also say that A is a theorem relative to the hypothesis gamma. So we call those relative theorems. Now today we're going to look at a few meta theorems. That means we're going to prove some statements about our proof, our system of proofs, right? So these are not proofs. These are not theorems. Like when you here call A is a gamma theorem, here say A is a theorem, but a meta theorem is a statement that we are going to prove about our proof system. So we are in our meta logic. So the first meta theorem is called the hypothesis strengthening. You notice that I proved the meta theorem for tautological implication that if you have two sets, sigma and gamma, and sigma is a subset of gamma, then if sigma tautologically implies a formula A, then gamma tautologically implies a formula, the same formula A, right? Meaning with more hypotheses, you can obtain more tautological implications. The same is true for our proof system. That means if, now here I changed the names from sigma and delta to delta, sigma and gamma to gamma and delta. So suppose gamma, which is a subset of the set delta, proves A, then with delta as hypothesis, which has more formulas in it than gamma, you can also prove A. And the proof is absolutely obvious because if you remember what the gamma proof was, a gamma proof for the formula A is a sequence of formulas that at any step you can write a member of gamma or an axiom, and then you can apply the rules of inference as well. But since gamma is a subset of delta, that means that any step I can write a member of delta in a delta proof, right? That means any gamma proof is by definition a delta proof. Sorry, I'm just going to switch this off. Just making noises. All right. So just from the definition of a gamma or delta proof, it follows that any gamma proof that we write is automatically a delta proof, because the formulas in gamma are included in delta. Therefore, if we have a gamma proof for A, then we have a delta proof. The same proof is also a delta proof, right? So this follows from the definition, and the corollary of this is when you apply the case for when gamma is the empty set. So a special case that gamma is empty set tells us that if A is an absolute theorem, Now instead of delta, I used gamma here. Then A is a gamma theorem for any gamma because empty set is a subset of any set, right? So any absolute theorem A is a gamma theorem for any gamma, for any set of hypothesis gamma. So that means absolute theorems are relative theorems, and we are going to use them, use this fact in our future proofs. And now the next important method theorem is called the transitivity of the proof. Now suppose, again, you have a set of formula called gamma, and gamma can prove formula B1. Also, gamma can prove formula B2, and gamma can prove formula Bn. So gamma proves n formulas, B1, B2, Bn. And B1, B2, Bn, together, they can prove a formula A. So these formulas can prove formula A. So usually when we have a finite set, we don't write the bracket. So this is the notation. So we have that these hypotheses, with these assumptions, we can conclude that gamma can prove A. Because gamma can prove these BIs, and BIs can prove A. Therefore, gamma can prove A. So this is something that is, again, it's quite obvious they should be true. And it is true, but let's look at the proof for this. And you can see that why this is called the transitivity, right? It's the transitivity of proof. This symbol, we call it a proof symbol. So you could just say this is a transitivity of proof. So let's assume we have our assumptions that gamma can prove these BIs. What does it mean that gamma can prove BI? Well, that means each BI is a gamma theorem, right? There is a proof for BI within gamma. So that any proof is a sequence of formulas, right? So gamma proves BI, where I is any number between 1 and n. What does this mean? There is a proof for BI, meaning there is a sequence that now I'm going to index this for any I. So I'm going to keep one index for I. There's a sequence of formulas CI1, CI2, CI, some here, I don't know, something, CIK, K also depends on I, so I wrote KI. And at the end, you have BI, because BI proves, BI is a gamma theorem, means that it appears in a proof. So it appears in the sequence. So we'll stop when it appears. So the last formula is BI. Now, when I is 1, you have a formula for B1. Sorry, you have a proof for B1. When I is 2, you have a proof for B2. The corresponding sequence is a proof for B2, and so on. When I is n, you have a sequence Cn1, Cn2, Cn3, Cn some k, and at the end Bn. That's a proof for Bn. Now, if you put all of these proofs together as a sequence to here, it's still a proof. It doesn't violate any of the steps for a gamma proof, because each of these does not. So we have a gamma proof for all of these BIs. Now let's use the last assumption that B1, B2, Bn can prove A. What does this mean? This means that if I call this set delta, there's a delta proof for A. Now let's write that. That means there's a sequence. Let's call that sequence A1, A2, AN that ends with A. So there's a sequence A1, A2. So let me write this. This implies that there's a sequence A1, A2, up to some AM, and then at the end, you have A. Right? So there's a sequence of formulas, which is a proof, meaning it satisfies those two steps that we required for a proof, or three steps that we required for the proof, that ends with A. Now, in this proof, BIs are going to appear somewhere. Maybe not all of them are necessary, but they would appear. And then there would be applications of axioms and rules of inference, but we don't care. Those are included in AIs. Now, if you attach that proof to the end of this sequence, now this whole thing is still a gamma proof. And since A appears in a gamma proof, that means A is a gamma theorem. Right? So this is about attaching the proofs together as a sequence and noticing that this is still going to be a proof, meaning it still satisfies those assumptions or requirements for the proof, and we have a proof for A. So this is called the transitivity of the proof. If you can prove a bunch of formulas, and those formulas can prove a formula A, then from your original hypothesis, you can prove A. There's a few corollaries of this. The next corollary, it's not a priori obvious why it follows from this transitivity, but I'll give another proof for this corollary, so it makes it clear. Suppose if you have gamma, again, a set of formulas, and you have a formula A, and now add A to the hypothesis, and you can prove B. So this means B is a gamma union A theorem. Now also assume that gamma proves A. So you can also obtain or prove A from gamma. Then gamma proves B. Again, it's clear that why this is called a transitivity, or it follows from transitivity. You're proving A from gamma, and if you added A to the hypothesis, you can also prove B. Therefore, since A can be proved within the hypothesis from gamma, then gamma alone should be able to prove B. Now, why does this follow from the previous theorem, the transitivity? By the way, I'm going to call this one also transitivity, since it's saying the same thing. All right. First of all, since gamma union A proves B, that means there is a gamma union A proof for B, right? That is a sequence that proves A using the hypothesis in gamma and also the hypothesis A. So there is a sequence. Note that one of the basic facts about the proof is that the proof is a finite sequence, right? So there's only finitely many of hypotheses in gamma are used even if the gamma was an infinite set, no proof can use infinitely many hypotheses. Any proof is finite. So at any proof, we only use finitely many hypotheses from gamma, even if gamma was an infinite set. So that means there are hypotheses from gamma, but only finitely many of them that are used in this gamma union A proof for B. So I'm going to call those elements C1, C2, Cn. So Ci's are members of gamma, that is their hypothesis. So take those finitely many that are used in a proof for B. Together with A, they can prove B. Now, since Ci is in gamma, it's a hypothesis. Gamma can prove Ci. There's a one-step proof. Any hypothesis can be proved within gamma. Any member of gamma is a gamma theorem. There's a one-step proof for it, right? Just write Ci. Now we also know, so this is for all. Sorry, let me write this a little bit. So we took these Ci's that are members of gamma, only those hypotheses that are used in the proof for B. And we know that gamma proves those. There's a one-step proof for each of these Ci's, but we also know that gamma can prove A. This is for any I between 1 and n. And we also know C1, C2, Cn, and A together, they can prove B. Now apply this theorem, where you have your BI's are C1, C2, Cn, and A. Each of them is a gamma theorem, and together they can prove B. Therefore, by the transitivity of the proof, gamma can prove B. Yes?
So we assume that gamma can prove A because A is a hypothesis.
No, A is not a hypothesis. We assume it because it's given to us.
Oh.
Yeah. A is not a hypothesis. I mean, A is a hypothesis here. But we are at the end, what are we proving? We are proving gamma proves B. In a gamma proof, A is not a hypothesis. That's why this is essential that it's given to us. Yes.
So could you re-explain what like the gamma union A, like what that represents?
It's a set. It's a set of formulas, right? Gamma contains a bunch of formulas. Let's call them, is a set of formulas, CIs, right? Let's call them DI. D1, D2, D3, could be up to DK, or it also could be infinite, right? When you add, well, I'm pretty sure you are familiar with the union of two sets. So now take the union with a singleton set, a set that contains one formula. Now, this is just a set that contains A, D1, D2, and all these DKs. Again, gamma could be an infinite set, could be a finite set, we don't know. But the proof doesn't depend on it because any proof only uses finitely many hypotheses. Now, those hypotheses that are used, I know there are finitely many used. They are used in a gamma union A proof for B. Let's call them C1, C2, Cn. We don't know how many they're used, but there are finitely many of them from gamma. There's also A that might be used, because this is a gamma union A proof, meaning it is essential to, in order to prove B, you might need A, right? So here, you need A to prove B. I mean, when I say you need A, you don't know if you do or not, but from what we know, it's essential to put it there because it might be used. Now, this extra fact that gamma proves A allows us to apply the transitivity. Now we know that if I added A here, I can prove B, but also gamma can prove A. So gamma can prove all of these CIs and A, and CIs and A together can prove B. Therefore, by transitivity, gamma alone can prove B. Yes.
My question was that the gamma union is we call it proof, but does it matter if A is finite or not?
A is a formula. A is not a set. What does it mean A is a finite or infinite? A is a formula. A is a single formula. Gamma is a set of formulas. All right, let's move on. So what does this corollary say? It actually says something very important that we are going to apply all the time in our previous proofs. In our next proofs. It says that if using bunch of hypotheses, a set gamma, I can prove a formula A. And let's say we have established this. We know that using these given hypotheses, I can prove a formula A. And then I want to prove the formula B. So I want to prove B from gamma. It's enough that I add this A as a hypothesis and use it as a hypothesis to prove B. And then this theorem tells me that I can take A for granted because I have already proved it. And if I know gamma proves A, and using A as adding A to hypothesis, I can prove B, then I have proved B. What does that mean? That means any theorem, any gamma theorem that we have proved already can be used in our following proofs. Right? That's the consequence. And this is how mathematics works, because you prove something and now you can use it. If you have the same hypothesis, now you can use it. And so this is a very essential fact in mathematics in general, that it's when you prove something, you can use it now. Your next proofs. Yes.
If gamma can prove A, right? And then we know then that we can use A to prove B along with gamma, right? So there's no point then in adding A as an hypothesis.
What do you mean there's no point? I mean, what this says that if you have proved A already and you wanted to prove B, you can add A as a hypothesis, right? having more hypotheses is only going to make the proof easier, right? Any proof is easier when you have more hypotheses. So you can use this fact that you've already proved. That fact is the formula A. It says something, a fact, right? So that's why I call it a fact. And it's proved already using this certain hypothesis that we call gamma. Then I can take it for granted, because we have already proved it, and treat it as a hypothesis. And if I can prove that another fact B, that means gamma alone can prove B. So we have a gamma proof for B. Yes.
Is adding A to the gamma set hypothesis strengthening?
No, hypothesis strengthening is something else, right? Hypothesis strengthening is this, that if you have more hypotheses, you can prove more, right? But I mean, this is not this. This is something else. This is not talking about like you can always note that the application is different. We wanted our goal is to prove gamma alone proves B, right? Yes, if gamma, if I knew gamma proves B, then yes, gamma union A proves B, but I don't want this. This is hypothesis strengthening. I want it the other way around, right? So this is very different from strengthening hypothesis. All right, let's move on. So now whatever we prove using the set of hypotheses, we can apply it in the following proofs using the same set of hypotheses. Another corollary of this is the following, that if gamma union A proves B, and A is an absolute theorem, then gamma proves B. So why is this a corollary of the transitivity? Well, if if A is an absolute theorem, now if you apply the strengthening hypothesis, so suppose A is an absolute theorem, then by strengthening hypothesis, I know gamma proves A. If you can prove something without a hypothesis, then you can prove it with some hypothesis. Now you apply the previous corollary. Now we have both this and this. Therefore, gamma proves A. So from the last corollary, we get gamma proves B. So what does this tell us? It tells us that when you prove an absolute theorem, then you can use it in any proof, no matter what your hypotheses are. So absolute theorems can be applied in any proof. So they're like axioms. Absolute theorems are theorems that could have been even taken as axioms. They're always true, no matter what your hypothesis is. So you can treat them like axioms. At any proof, if we have proved something with no hypothesis, we can use that thing in our proof, no matter what the hypotheses are. All right, that's exactly what I talked about. This is a comment about absolute theorems that we have already been talking about. So, and this is what I said, that in general, this meta theorem that we call the transitivity of the proof and strengthening hypothesis. So these are two very important meta theorems that we talked about today. Together, they imply the following fact. So this is essentially what we get from putting these two together, that in any gamma proof, we can use previously proven delta theorems if we know that delta is a subset of gamma. Meaning, if we have proven a theorem, let's call it A, from, let me write this down. Suppose we want to prove gamma proves the formula B. And we know, that means we have already proven that with a delta, we can prove A for some formula A, where delta is a subset of gamma. Then we can use A in the gamma, in any gamma proof for B. Yes.
Doesn't that imply that gamma proof A?
Yes, it does. That's why we can apply it. So this, as you mentioned, implies by strengthening hypothesis that gamma proves A. That's why we can use it, right? Because gamma is A is proved with from delta. It can be proved using hypothesis in gamma because delta is a subset of gamma. So we can use it in the following proofs. All right. So this is an important fact, and it justifies why we are proving theorems now. We are proving a lot of theorems, and that is going to allow us to use those theorems in proving more theorems. So we're building a toolbox of theorems that is proving a lot of things. And we extend the toolbox by proving any theorem. We are extending the toolbox, so our proof abilities every time is improving. So let's prove some new things. First of all, this one is pretty much obvious. Note that we had equanimity as one of the rules of inference. It told us that if I have A, and if I have A is equivalent to B, then I can prove B. Now, what happens if I swap the order, and if I have B here, can I also prove A? It's just the other way around. You just apply it with a different order, and that's called the other equanimity. And later on, we're just going to call this also equanimity. And it's obvious. It follows from equanimity itself and symmetry of the by implication symbol. So what's the proof? At step 1, I'm going to write B because the hypothesis. Step 2, let's write the other hypothesis. Again, this is a hypothesis. Step 3, I'm going to write an axiom. A is equivalent to B is equivalent to B is equivalent to A. This one is an axiom that is called associativity symmetry, symmetry of equivalence. Now, step 2 and 3, I can apply equanimity. And I can get B is equivalent to A. Now, step 1 and 4. Apply the usual equanimity again. If you have B and B is equivalent to A, you get A. Any questions? So now we did this so that we don't want to care about the order of how you apply the equanimity. If you have A, or if you have A and B is equivalent to A, you can always just conclude the other one, which is B here, regardless of if this is A is equivalent to B or B is equivalent to A. The order now doesn't matter because we have both, and we're going to call it equanimity in general. Right? So now that we proved this, we can apply it. Let's recall a theorem that we proved last time. This was the transitivity of the equivalence symbol. We proved that if A is equivalent to B and B is equivalent to C, you can prove A is equivalent to C. We proved it using Leibniz. Now this is, I just wrote it for us to remember what we have proved so far. Note that this can be taken as a secondary rule of inference, right? If you just think about it, even though we're not going to really care about this so much, but sometimes in some other textbooks, they might take this as a rule of inference as follows, that if you have A is equivalent to B and B is equivalent to C, then you can conclude A is equivalent to C, right? These kind of theorems that are essential and important, they can be treated or regarded as a secondary rule of inference, but we're just going to, just something that we have, we're going to use it in the future. Another theorem that we proved last time was the reflexivity of the equivalence symbol. We proved that A is equivalent to A is an absolute theorem. We can prove it with no hypothesis. That means this now can be used in any proof that we want. And this is not just about the letter A, this is for any A. This is a schemata, right? It's a it says that for any formula A is equivalent to A is a theorem. In particular, apply to anything. Top is equivalent to top is a theorem. B is equivalent to B is a theorem. If P is a variable, P is equivalent to P is a theorem. And we have proved all of this. In particular, the one that I wrote here, that bottom is equivalent to bottom, where A is bottom here, is an absolute theorem. That means I can apply this in my next proof. What do I want to prove? I want to prove that top is an absolute theorem. Top is always true, so it should be an absolute theorem. But how do you prove it using our system? How you write a proof for this? You can write it like this. How about starting with an axiom called top versus bottom? Top equivalent to bottom is equivalent to bottom. This was an axiom. I think we called it top versus bottom. Now, we put the brackets here, but we also have associativity, right? We know that top equivalent to bottom is equivalent to, so this, I'm going to put the brackets here. This is equivalent to top is equivalent to bottom is equivalent to bottom. This is the associativity of equivalence, which was also an axiom. Apply the equanimity here. The only reason that I did this, I wanted to get top is equivalent to bottom equivalent to bottom, and now I know bottom equivalent to bottom is an absolute theorem. So this is from step 1 and 2. We applied equanimity, a rule of inference. Now, step 4, what do? I already know that bottom is equivalent to bottom is a true statement because it can be proved, right? I have it as a theorem. I've already proved it. And from what we said here, we can use, as a consequence of strengthening hypothesis and transitivity of proof, those two meta theorems tells me that whatever I have proved, I can use it in my next theorem as long as the theorem that I'm dealing with has more hypotheses than the hypotheses that are used to prove that theorem that I want to use. And that means if I have proved an absolute theorem, that means I can use it in any proof. And here I have an absolute theorem. I can use it in any proof. I'm just going to call it here, the annotation that we use. We just write a theorem or absolute theorem. Just to be more precise, absolute theorem. We can use it, as I said, just like a hypothesis or an axiom. Now, I think it's clear. Now, equanimity, that's the other equanimity, but we're just going to call it equanimity. We can get top. Top is equivalent to bottom, equivalent to bottom. We also have bottom equivalent to bottom. Therefore, we can write top. So steps 3 and 4, equanimity. Any questions? Yes. Yes. I mean, we are not. I mean, we already proved this. We know it's true, and the strengthening hypothesis. And in this case, there's no strengthening hypothesis because I don't have a hypothesis here. So just the transitivity of proof tells me if in any proof for top, I can add this just like a hypothesis, right? So in the strengthening method theorem that I said here, gamma would be empty set, and the formula A would be this, and I want to prove formula B, so I can add A to the hypothesis and prove B, which is top here. Now again, another kind of rather obvious theorem, but we're proving obvious theorems so that we can use them and in the future proofs without worrying where they came from. Here is equanimity plus Leibniz, that we can apply these two together at the same time in one step in the future, that if we have the formula C where the variable P is replaced or substituted with the formula A, and we know that A is equivalent to B, then we can conclude or prove C, where the variable P is substituted with B. And note that this is again very obvious, because when we have this formula as a hypothesis and we also know A is same as B, then we can just replace A with B here, then we get this formula. So let's just practice writing proofs. Step 1, I can write hypothesis. Any step we may write a hypothesis. Just right here, this is a hypothesis. Step 2, I will write the other hypothesis as well. Now step 3, if A is equivalent to B, Leibniz tells me that in any formula C, if I plug in A for B, it's equivalent to C when I plug in B for P. So this is from step 2, Leibniz. Step 4, I think it's obvious. Now we apply the equanimity to step 1 and 3. Right, so this was a very simple proof. Let's prove again more trivial things. The other associativity, note that the associativity that was an axiom for this equivalence, it looked like this. Actually, I've written it in step 1. If we have the formula A is equivalent to B is equivalent to C, it's equivalent to A is equivalent to BC. B is equivalent to C, right? But now we want to be able to apply this the other way around, meaning swap the order of these two. So that is A is equivalent to B is equivalent to C is equivalent to A is equivalent to B equivalent to C. And it's obvious when you want to swap the order, you want to use the symmetry, right? So that's what we're doing. Step 1, the axiom itself. Step 2, this whole axiom by symmetry is equivalent to when I swap these two. So here I have swapped this with this. It looks like a complicated formula, but it's just really the axiom of symmetry. This formula here, which is step 1, is equivalent to the formula when I have swapped these two, this with this. And we know it as an axiom that this is true. A is equivalent to B is equivalent to B is equivalent to A. So we can always swap the order, the equivalent. So we wrote the axiom itself for properly chosen formulas AB. Now I applied equanimity and we can get this, which is exactly associativity, but now it's the other way around. Yes. You have a question? Yes. Well, here we didn't use any hypothesis here. We used an axiom.
So then,
We didn't have any hypothesis, right? Hypothesis is the empty set. So we started axiom, but which axiom should we start with? I mean, we want to prove the associativity, and it's just a reflection of associativity. So it's obvious that you want to start with associativity axiom. Now the reason that I proved this is that now these two associativities combined, now we're going to call both of them from either direction just associativity of the equivalence symbol. Together they tell us that when you have a sequence of equivalences, it doesn't matter if you put the brackets here and then here or here or whatever, wherever you want to put the brackets in between these. That means which operations you do first. First, you construct A is equivalent to B, and then A1 is equivalent to A2, and then A3 is equivalent to A4, and then take the maybe equivalence this one next, or no, you apply this first, and then apply this second. There are many ways to do it, but they're all equivalent. Applying the associativity finitely many times, they say that by changing the brackets between these consecutive equivalences, every time you end up with something equivalent. So in the future, we're not going to bother with this. We don't want to write this applications of associativity so many times. It's just extra writing. We want to avoid writing trivial things. In the future, we can put the brackets anywhere we want, and without even mentioning that we are using associativity finitely many times. So for example, I had this axiom called axiom of symmetry, right? It was written like this: A is equivalent to B is equivalent to B is equivalent to A. And the brackets were here. This was an axiom. Now, I know using associativity, for example, this is the same. It's the same axiom because it's equivalent to what I want. So it's an absolute theorem now. We identify it as an axiom, right? It's the same. It's saying the same thing. Just associativity applied to it, I think, twice. So between consecutive equivalences, we can put the brackets here, or no, if you want to put the brackets, for example, A is equivalent to B is equivalent to B is equivalent to A, put the brackets here. And well, if you want to be even more careful, put the brackets here first and then here, and then so on. It doesn't matter. So next theorem, prove that A is equivalent to A is equivalent to B is equivalent to A. Now you notice that this is exactly the same as the axiom that I just mentioned, the symmetry, but it was written like this. Put the brackets anywhere you want. Now what's the difference between this theorem and this? Well, there's only one difference. This A that's jumped here. How do I take that A there? I apply symmetry. So start with the axiom of symmetry. Note that now I put the brackets the way that I I want. So starting with axiom. Now, how do I take A here? What if I swap this A with this entire formula here? There are many different ways to do it, but you can do it in 2 steps by moving, but maybe applying the symmetry to this part and swapping A and B, and then doing it in another step, swap this and this. But why don't we do it in 1 step? We can swap the whole A with A is equivalent to B is equivalent to B. So we know that it's an axiom, again, axiom of symmetry, that this is equivalent to when you swap A with this entire formula, which is A is equivalent to B equivalent to B. But now apply the equanimity. You have this, same thing is equivalent to this. So you can get the other side. Yes.
We don't have a hypothesis there, right? And we're just using that, right?
Yeah, we don't have hypothesis.
For the practical one.
Yes.
Then is that the thing for the position of A on the start? Like, why do we-
Now position of A, it wasn't about the position of A in the previous. Here, this associativity here did not allow us to change the position of A. But now we are proving that we can change the position of A the way that we want. And that's what just by applying the symmetry.
So that's why you started with the name that it's just.
I started with what I had, right? What we have is only axioms and hypotheses in the beginning. You can't just change the position the way that you want. It's only about what you already have proved or what you have in your toolbox. But now I have this because I proved it. I know that A is equivalent to A is always equivalent to B is equivalent to B for any formula A and B. Yes. There are different ways to prove this. Yes. I don't know if there are only 2 ways. You can always add even extra steps, even irrelevant steps, right? That's the thing for the proof. I can write here also top in this first step. Is it relevant? Step 0. But I have already proved top, so I can add it, right? The proofs are, for anything, there are infinitely many proofs, according to the way that we define. It depends on you if you want to write the most efficient proof, or just add a bunch of nonsense that you don't even require in a proof, right? But essentially, yeah, there are like 1 or 2, maybe 3 different efficient ways to prove something, or like at least this one. Yes. All right. Do we need to do a step 2? In the future, we might skip step 2, right? And just here, write the axiom of symmetry. We apply the equanimity to it. But for now, we are being syntactically careful, and we write every step. At any step, you may write down an axiom or hypothesis or a theorem that you have already proved. And if I just skipped to step 3 without writing step 2, it's not clear where did this come from. It came from another axiom and equanimity. So we are being a little bit careful in the beginning. In the future, when we write more proofs, you might skip step 2. Now, this is true for any formula A and B. What if, for example, A was top? The corollary of this theorem is that top is equivalent to B is equivalent to B. What if B was bottom? Another instance of this theorem is A is equivalent to A is equivalent to bottom equivalent to bottom. You can make a lot of instances like this. these two are, I've written them because I want to use them in the next proof, next theorem, that is called the redundant truth. It's actually two of them, but they're almost identical. They're symmetric. Top is equivalent to A is equivalent to A is an absolute theorem. And you want to understand why this should be always true. A is equivalent to A should be always true. Therefore, it's true. You should be able to prove this, that A is equivalent to A is always true. And this says the same thing with a different order, that A is equivalent to A is equivalent to top. Now, how do you prove this? For the first one, for this one, we know top is an absolute theorem. I can use it in any proof. We already proved it. So step one, absolute theorem. Step two, this, we already proved this. So apply it for A when A is B. So top is equivalent to top is equivalent to A is equivalent to A. So it's a theorem, absolute theorem that we have proved. We can use it. Step three, apply the equanimity to this. You have top, top is equivalent to this. You get top is equivalent to A is equivalent to A. For the second one, the proof is similar. You can write a similar proof, or you can use what we just proved. We just proved that top is equivalent to A is equivalent to A. Again, by associativity, I could think of it this way or this way. They're all the same. I don't even bother writing brackets here. Then you have a sequence or a consecutive equivalent formulas. Now just apply the symmetry, right? Top is equivalent to A is equivalent to A. Think of it this way. Symmetry allows me to swap the order of these two. So this equivalent to A is equivalent to A equivalent to top. Now I apply the equanimity to step 1 and 2. We get this side of the equivalence. So this redundant true is kind of actually an important one. And we are going to use this one more often in our next proofs. Let's pause for a second with these proofs. These were a bunch of obvious theorems that should be true, and they are true. But let's prove a few more meta theorems. That means we're going to prove a bunch of more facts about our proof system. Now, for any set of formulas, gamma, if we have a formula A, then gamma proves A if and only if gamma proves A is true. A is equivalent to top. So that means if whenever you prove A, in fact, you have proved that A is equivalent to top. So in any gamma proof, for A, which means A is a gamma theorem, we have in fact proved that A is equivalent to top. Now, why this follows, first of all, you have two directions, but both directions are consequences of this redundant truth that we have. So let's look at the forward direction. I'm going to assume gamma. So for the forward direction, assume gamma proves A. I also know that A is equivalent to A is equivalent to top. That's the redundant true here. right? We have proved it. It's an absolute theorem. Well, if it's an absolute theorem, by strengthening hypothesis, it's also a relative theorem relative to the hypothesis gamma. So gamma can prove the same thing. Now apply equanimity to this step, to this and this, apply equanimity. In one-step proof, or it's actually 3 steps. You write A, you write this. Actually, I really didn't need to have to use strengthening hypothesis, but I did because this could have been done in literally a proof rather than arguing like this. When I say it can be done as a proof, I can write the proof like this. Rather, I can write step 1, A. Why can I write it? Because it's a gamma theorem, right? It's a hypothesis that we are assuming A is a gamma theorem, so we can write it. Step 2, at any step I said I can write an absolute theorem. Step 3, apply equanimity to step 1 and 2. So that's an alternative proof. Here I gave a proof in a method theorem rather. For the other direction, the proof is the same. Now suppose, so for the other direction, now suppose gamma proves A is equivalent to top. We want to show that gamma proves A. So this is a gamma theorem. I also know A is equivalent to A is equivalent to top is a gamma theorem. No, sorry. Well, it's a gamma theorem because it's an absolute theorem. So it's an absolute theorem, I can use it. Now apply equanimity to this, I can get A. So A is a gamma theorem. So these are alternative proofs. Here I've written the proof probably a little bit more complicated, explaining a little bit more, but you don't have to. This is obvious. It's basically application of redundant truth and equanimity. That's it. Now, a consequence of that is the following theorem, that if you have a set of formulas gamma, and you can prove A and B from gamma, then this implies gamma proves A is equivalent to B. And before I write the proof, I'll just convince you that this is really a consequence of what we just said, because from here, I know gamma says that A is equivalent to, then I can prove A is equivalent to top. And from here, I can prove that B is equivalent to top. Or B is equivalent to top, let me write it like this. Now apply the transitivity, right, of thing. A is equivalent to top, B is equivalent to top, therefore A is equivalent to B. Now let me write this properly. So I want to write a gamma proof for A is equivalent to B. So let's write a gamma proof. Let me write this. We write a gamma proof for A is equivalent to B. Note that we are assuming that A is a gamma theorem, B is a gamma theorem. Step 1. What I do, the transitivity of proof told me that if you have proved the gamma theorem, you can use it in a gamma proof. And I know a gamma theorem, A, so I can use it. A, why can I write A? Because there's a gamma proof for it. So I'll just write gamma theorem. Right, this is a consequence of the transitivity of proof, right? That we can, something that is given to us, something that we already know is a gamma theorem, can be treated as a hypothesis. Right, we could add it just like a hypothesis in our proof. That was the first meta theorem that we proved today, or actually the second one after the strengthening hypothesis. So I have this. I also have maybe before I write the proof, because all right, before I write this, let me establish that since gamma proves A, by our previous theorem, we know that gamma also proves A is equivalent to top, right? This was this theorem. And since gamma proves B, I know that gamma, I don't have to write since, gamma proves B implies gamma proves B is equivalent to top. Now let's write the proof. Step 1, I know A is equivalent to top is a gamma theorem because A was a gamma theorem. And we know if A is a gamma theorem, then A is equivalent to top is a gamma theorem. Now B is equivalent to top is also a gamma theorem here. Now apply the symmetry. No, sorry, not the symmetry, the transitivity. 3. Transitivity, not of the proof, but of this. It's a different transitivity, right? We proved it. And since the hypotheses of the proof are written, we can get the consequence. This again, applying the transitivity of proof again, right? If this hypothesis are already proved, then we can apply it. A is equivalent to B. Any questions? Now this step maybe requires a little bit more explanation if I wanted to be very picky here. Why am I using, why am I allowed to do this? I know that if I have A is equivalent to top and B is equivalent to top, I can prove A is equivalent to B. This was transitivity that we have proved. We proved it last time. But why can I use it here? It's because these are already proved. So gamma proves this. Note that gamma proves A is equivalent to top, and gamma proves B is equivalent to top. And remember, when gamma proves two formulas, B1 and B2, and B1 and B2 together, they can prove a formula. Then gamma can prove that formula to transitivity. Of proof tells me that I can conclude. So let's write this properly. I want to have this properly written. The method theorem that we prove implies gamma proves A is equivalent to B. Right? So we applied our method theorem. I didn't say here I used the transitivity of proof here, but we understand that. Why we are allowed to use the theorems that we have already proved. It's because of the transitivity of the proof system. Right? Yeah. Sorry? Yes. Yes. All the axioms are tautologies. Therefore, they're equivalent. All tautologies are equivalent. I mean, if I wanted to explain it semantically, right? But here we are not dealing with semantics. That's why we require proof. But now we have the proof for this. That so the question was, if all the axioms are equivalent to top, the answer is yes, because all the axioms are absolute theorems. Therefore, all the axioms are equivalent to top. And that means all the axioms are equivalent. In fact, all the absolute theorems are equivalent to top, and therefore equivalent to each other. Yes. Real life example of this proof. Now that's a difficult thing, but these are note that these are very, very abstract and syntactical things, right? But in fact, they stem from very, very basic and important things in mathematics or even computer science. That this really what it says that is that all the tautologies they're equivalent to each other and they're equivalent to truth, right? So no matter what tautology you get, a tautology like negation of P equivalent to P, sorry, like this one or P, or another tautology like what else? Like top is equivalent to top is equivalent to top. They're equivalent to each other. And this is very important fact that they're semantically the same. And now we can actually show that they're syntactically the same. So even though the things are very syntactical and abstract here, but what we are proving are very, very important facts about general mathematics. All right, I think we're out of time. Next time we're going to talk about another proof method called the equational style. And we learn how to write equational style proofs. Have a nice day, everyone. See you next week. No, this week. No, next week. Sorry. I forgot. Yeah. Yes.